In this example, we're told we have a gas contained in a rigid closed tank fitted with a paddle wheel, so let's sketch that out. We've got this tank. There's a paddle wheel that's coming inside here. There's gas in here. The walls of the tank are rigid. And we're told the paddle wheel stirs the gas for 20 minutes with the power varying with time according to what's given right here, 10 watts per minute times the time. So what that means is that the power being done on the gas is 10 watts per minute times the time. We're also told that heat transfer from the gas to the surroundings takes place at a constant rate of 50 watts. So there's actually, I'm going to draw the heat transfer going this way into the system, but since the heat transfer is actually going into the surroundings, that will be a minus 50 watts, right? Because it says heat transfer from the gas to the surroundings. So if I've drawn the heat transfer into the gas here, then it should actually be a minus 50 watts because it's really coming out. By the way, I should probably draw the work being done on the gas as well. In that form. And then what we're asked to find is determine the rate of change of energy of the gas at time t 10 minutes, and what's the net change in energy of the gas after 20 minutes. So the way we're going to do this is we're going to apply the first law to a control volume that surrounds the gas. So let's write that out. Our first law. And I'm going to write the rate form of the first law because in part A we're trying to find the rate of change of energy. And when I write the first law, I'm going to do the plus rate of work done on the system. Since I know that I'm doing work on the system here with the paddle wheel, then I'm going to just use the plus work done on the system. So we know the values of some of these terms. So the rate at which energy is added via heat transfer is actually a minus 50 watts. And the rate at which work is done by the paddle wheel is 10 watts per minute times the time. But we're told that we want to find this rate of change of energy of the gas at time t equals 10 minutes. So our t here will be 10 minutes. Notice that this minute will cancel with that minute. And so when we multiply this together, we'll get 100 watts minus 50 watts. So our rate of change of energy within the system will just be 50 watts. So that's part A. Now part B, we're asked to find the net change in energy of the gas after 20 minutes. So that form of the first law will look like this. We're trying to find the change in energy of the system. So what we want to do is determine the total energy added via heat transfer plus the total work done on the system. And the way that we'll calculate both of these is we need to do an integral. So the total energy coming in via heat transfer over the 20 minutes would be just integrating the rate of heat transfer coming in over the time where t goes from 0 to 20 minutes. And then to find the rate at which work is being done, we'll integrate that one as the power as well. So again, from t goes from 0 to 20 minutes. And this will be the 10 watts per minute times the time times dt. So we're just, to find the total amount of heat transfer and work, we're just integrating the rate of heat transfer with time and the rate at which we're doing work with time. Now here, the only thing we have to be a little careful of is to do the unit conversions properly. So with the rate of heat transfer, remember that term is a constant. We're told that it's a minus 50 watts, so it can come outside the integral. So we'd have minus 50 watts times, and then what would be left over in the integral would just be the integral dt, so that would just be 20 minutes. But you have to be careful because watts are in joules per second, and we have minutes here, so you'd want to multiply this by 60 seconds per minute to do that calculation. And then the rate of work term we can integrate that one as well. So the 10 watts per minute will come outside the front because it's just a constant, and then we're left with the integral of t dt. So that'll just be 1/2 t squared, and we're going to integrate that from 0 to 20 minutes. Now this one, we don't have to worry. Well, we still have to worry about changing the minutes to seconds. We have to be a little careful of that because one of the minutes will cancel out with that minute, but then we still have to be careful with the watts. So I won't do those steps here, but you have to be a little careful of the unit conversions. But if you're careful with those and you work out the rest of the problem, just work out the numbers, what you'll get is this will be 60 kilojoules after 20 minutes. Okay, so both parts of this problem involve applying the first law. The first one involves just the rate form of the first law. The second one involves the kind of before and after form of the first law. The things to be careful of are making sure you get the correct sign on the rate of heat transfer term, being a little careful with some units when you do the power term. The units are more important when you're doing the before and after case where you have to worry about watts and minutes. And then finding the total energy added via heat transfer and the total work done by the paddle, you just have to do an integral over time. Okay, we'll end that example there.